Okay, so in this video, we're going to look at matrix creation and printing the matrix. Also look at some matrix operations in this file as well as the next Julia file. So we will use this random numbers package to generate matrix of random numbers. So let us add the statement using random. I'll come to this function print matrix soon. First, let me show you how a matrix is created. Okay. So this is how you could generate a matrix of random integers in this case. So 10 to 20 is a range and 3 by 4. So 3 rows and 4 columns. So if you remember for the vector case, if you want to create a random vector of integers, let's go to here. So the syntax is this. You have to specify the range and the number of integers you want in that vector. So same idea here, you specify the range and the size instead of 1 dimension. Here you specify 2 dimensions. So for integers, this is the syntax. Specify the range first to the rand function, which is in this case 10 to 20, and then the dimensions. If it's a 1 dimension vector, just specify the number of elements you want in that vector. If it's a 2 dimension matrix, in this case, you specify the number of rows followed by the number of columns. So this would create a 3 by 4 matrix of random integers in the range 10 to 20. Okay, so let me print it and then we'll go over the output. Okay, so if you just see how this println function of for this matrix 1, which we just created as a matrix of random integers, is getting printed, this is how it's getting printed. So 15, 16, 12, 11. That's the kind of the first row. Remember, this is a 3-row, 4-column matrix. This is the second row, and this is the third row. So it's printing row-wise. Okay, so each is like a row vector, we can say, and each row has 4 columns corresponding to the 4 columns in the matrix. So that's how if you just call println of on the matrix just created using the random number generator will get printed. And that's how typically all matrices in Julia are going to get printed as a sequence of row vectors separated by this semicolon symbol. Now, there is a function called size that you can call on a matrix, and the size will return a tuple corresponding to the number of rows and the number of columns. Okay. Now, in this case, number of rows is 3, so n rows will be 3 and n calls will be 4. So you can print the values of n rows and n calls separately if you want to. So the number of rows is 3 and the number of columns is 4. So if you want to print the individual row vectors, this is how you could do that. Now, any element in the matrix is accessed like the row index, comma, column index. So matrix 1 is the matrix we just created. And if I want to access, say, the element in the second row, third column, you could access it like this. So in general, it is accessed using the row index, comma, the column index. Okay. Now, if you want to access all the elements in a particular row, okay, so that means basically you want to extract a row vector, that's what we call. We can do it like this. So specify the row index you want to access, put that comma, and instead of putting column index, you can put something like this to access all the elements at a particular row denoted by row index. So this will return kind of like a, we can say a row vector. Okay. So if you want to write a program that will print the rows of a matrix as a sequence of row vectors, which it already does in this print statement. But we want to separately print, say, per line or access each row vector, then we can run a loop for row index in 1 to n rows. In this is a way one way to run the loop, 1 to n rows, the range of values for the row index. And then say row index is, so it means like row 1 is this. So this is how, as I said, you can access the matrix name, in this case matrix 1, and row index, comma, to access all the elements in that row, just put, or we can say all the columns in that row, just put colon symbol. That will retrieve all the elements, columns in that row. Now, similarly, if you want to access all the columns, sorry, if you want to access all the rows in a particular column, so in that case, we need to know the column index. So the column index follows the comma. So you can put comma column index. And for the row index, you can put just this column symbol. Okay. And that would retrieve all the row values in a particular column specified by column index. So in this case, we can extract a column vector. So you will run a for loop for I equals for I in 1 to n calls in this case, and specify the column index, the matrix 1. Okay, that will do. So if you see the output, that's what I'm showing here. So the first row is 15, 16, 12, 11, that's row 1. Then 17, 12, 14, 10, that's row 2. And then 18, 15, 15, 14, that's row 3. So if you want to access column wise, this is like 15, the first, this is like in row 1. So looking, first column means all the first elements in each row. So if you even look at it here, this is the first element in row 1, first column in row 1. This is the first column in row 2. This is the first column in row 3. So I want to print this together. So this will be like 15, 17, 18 now, because you're extracting this as a column vector across all rows. That's what this statement does. We're extracting it as a column vector across all rows. Similarly, you can print 16, 12, 15 as a second column vector, and 12, 14, 15 as a third column vector, and 11, 10, 14 as the fourth column vector. Now, you want to print it like this, the traditional way we print a matrix or write a matrix. So for this only, I had created this print matrix function that was there. So to this function, we just pass the matrix, because using the size function, we can always get to know the number of rows and number of columns in that matrix. So we don't need to pass this number of rows and number of columns as parameters to this function. So just pass the matrix, and we need to know as a developer that the argument passes a matrix. So once you get the number of rows and columns, you can again first get in each row, and in each row you print each column value, and then print a new line. That's kind of the classical idea. So for row index in 1 to n rows, and then run a for loop that goes into that row and prints each column value. So for call index in 1 to n calls, and basically print the individual cell value, that particular row index and column index, followed by a blank space. So this would basically go to the first row and print each of these column values separated by a blank space, 15, 16, 12, 11, and that's what is shown here. And then you print a new line after you come out of this inner for loop that prints the first row. You print a new line, so the control goes to the new line here, and then goes over the second row. So row index is 2, and then prints all the elements in that column, 17, 12, 14, 10. And then gets again print a new line, then go to the third row and print all the elements in that row, 18, 15, 15, 14. Okay, that's how this print matrix function prints the matrix. Then, like we saw a one-dimensional case where you can have an initial vector of all zeros or all ones, you can fill with any random default value. You can now have function or functions, yes, that can fill for you initial matrix of all zeros or all ones. So there's a function called zeros to which you pass the number of rows and columns you want to create as a matrix, and all those entries will be filled with zeros. So you can call this a zero matrix, just my name, but basically all the cells will be filled with zeros. That's why the function is called zeros. So if you print it out using our print matrix function that we just wrote, it will neatly fill it as zeros. And by default, it's treated as a float data type. So it will be printed with 0.0 when you try to print it. And then similarly, there is a function called ones, to which you can pass again the dimensions, the number of rows and columns, and it will create a matrix whose elements are all one each initially. Now, if you want to create a matrix of what do you call so this way you can create a matrix of all zeros. This way you can create a matrix of all ones. So these two functions will take care of that. But in case if you want to create a matrix of random numbers from 0 to 1, that random number matrix, for example, then you can specify rand. Again, in the case of one-dimension vector, you are passing just the number of elements you want in the vector. Each element will become 0 to 1. So here, just pass the dimensions. So you can say 3, 4, and then you can print using the print matrix function, the rand number matrix. So let's see what it gets generated. Yeah, so this is a matrix of the random numbers, 3 rows and 4 columns. Okay, so if you want, you can create a separate print matrix function that for the if the matrix has float as its data type, you can make it a formatted print if you want to, using the printf function syntax that we saw earlier. Okay, so that's about this file 15 on matrices. Let's go to file 16. Now, this is where I use some functions on the matrices, so like matrix operations. So all those functions are implemented in this package, linear algebra. So you make sure to write the statement using linear algebra, in addition to using random if you want to create a random integers matrix. Now, again, this linear algebra is part of the package in this file. So make sure you run this and get all the packages installed and updated before you run this. Okay. All right. So I have the same print matrix function written here to print the matrix. So this will be a very handy function that will print the matrices in a formatted fashion. Now there's a second function which will soon come and look at it. But let's go through the code outside the function declarations. Okay, so this is where things start. So I'm creating now what's called a square matrix. In a square matrix, the number of rows will be equal to the number of columns. And this is how you could do that. And again, a square matrix of random integers ranging from 10 to 100. So first you specify the range and then the dimensions, number of rows and columns. And then I can call the print matrix function and print the matrix. So let's see how it gets printed. So this is how it gets printed. Okay. So each element in this matrix is from 10 to 100, 4 rows and 4 columns. Now there is a notion called eigenvalues and eigenvectors of a matrix, which I'll introduce through this slide here. So for any square matrix, like which means number of rows and number of columns are the same, we can compute what are called the eigenvalues and eigenvectors for the square matrix. And the number of such eigenvalues, and so basically each eigenvalue will correspond to an eigenvector. And the number of such eigenvalues and eigenvectors you can find for a matrix will correspond to the dimensions of the matrix. So if you have, say, a 4 by 4 matrix, then we'll have 4 eigenvalues, and for each eigenvalues, we'll have a corresponding eigenvector. So what are those eigenvalues and eigenvectors? How they're related to a matrix? So if A is a square matrix, like in this case, an n by n matrix, then we can always find an eigenvalue denoted by, say, lambda, and a corresponding eigenvector denoted, say, by this x, such that A times x equals lambda times x. Okay, so when you multiply A, which is a square matrix, by this x, which is a vector, and it will be like a column vector, okay, and it's called the eigenvector. The product of these two will also be equal to the product of this eigenvalue, which is just a number, we call this a scalar value, multiplied by that column vector. So I show that here. So if 3, 2, and 3, -2 is my square matrix A, then there is an eigenvalue 4 for that square matrix, this square matrix here, and the corresponding eigenvectors, say 2, 1, such that the matrix A times its eigenvector, as I said, it's a column vector, 2, 1 in this case, would be equal to, so the product of these two, the square matrix and its column vector, would be equal to the product of the eigenvalue 4 and the same column vector, the eigenvector, which is 2, 1. So how can we verify this relationship or this equation? So that's what I'm going to show now. So for that, we need to know how to do matrix multiplication. So let me walk over that. So we cannot just multiply two arbitrary matrices of any arbitrary dimensions. So if you want to multiply two matrices, say matrix A multiplied by matrix B, now the dimensions should satisfy some conditions. So let's say the number of rows here is 5 by 6. Well, let's make it simple. Let's say it's a 3 by 4. And this is, say, a 4 by 5. So if you want to be able to multiply two matrices, the rule is this. The number of columns in the first matrix, okay? So let's name it as first matrix to make it very easy to remember. So the number of columns in the first matrix should be equal to the number of rows in the second matrix. This should be the condition that needs to be satisfied. The number of rows in the first matrix should be equal to the number of columns. The number of columns in the first matrix should be equal to the number of rows in the second matrix. So for two matrices to be multiplied, this should be the condition. The number of columns in the first matrix, which is 4 in this case, should be equal to the number of rows in the second matrix. And once you verify that, you can also specify. So when you multiply two matrices, what you get can be called like a product matrix. We can right away get the dimensions of the product matrix once you know the dimensions of the two matrices you want to multiply. So the dimensions of the product matrix in this case will be 3 by 5, which is basically the other two dimensions. So this 4 is the common dimension. So the product matrix will be of dimensions 3, which is the number of rows in the first matrix, by 5, which is the number of columns in the second matrix. So that's like a very important rule to be satisfied in order to decide whether you can multiply two matrices or not. Like if you want to now check here, can we multiply these two? So you can treat this vector as a matrix for this multiplication purpose. So the let me do this. The square matrix A multiplied by the eigenvector. So A is a 2 by 2 matrix, 2 rows, 2 columns. The eigenvector, as I said, is a column vector, so it has 2 rows and 1 column. So it's a 2 by 1 matrix, 2 rows the column vector has that many rows corresponding to the number of rows there, and that one column. That's why it's called a column vector, since it has one column. So the product matrix. Now you can multiply them because the number of columns in the first matrix equals the number of rows in the second matrix. Okay, that's a common dimension. So the product matrix will be of dimension 2 by 1, where the 2 here corresponds to the number of rows in the first matrix A, and the 1 corresponds to the number of columns in the second matrix here. Okay, so if you multiply this 4 scalar times this 2, 1, which is a 2 by 1 column vector, is basically the 4 multiplied inside each element. So 4 times 2 is 8, 4 times 1 is 4. So the 8, 4 that you get is basically a column vector of dimensions 2 by 1, 2 rows, 1 column. Okay, so this is the first thing that we have to check here. Then once you know that two matrices can be multiplied and we can get a product matrix, we need to fill the product matrix. So how would we fill the product matrix? So the rule is this. So if you want to get, so let me just call P as the product matrix. If you want to get row I, column J value, so this is a particular cell value at row I, column J in the product matrix, then you have to multiply the elements in row I of the first matrix with, let me put it like this way. Pairwise multiplication of elements in row A of the first matrix with the elements in column J of the second matrix. Let me just say call J of the second matrix, followed by the addition of all the product pairs. So what it means is this, let me use an example. Let's pick up the same thing we had here. So let's create a random integer matrix of dimensions 3 by 4. I'm just avoiding the negative numbers to keep the math simple. You could have negative numbers. So this is a 3-row, 4-column matrix. And this is a 4-row, 5-column matrix. Five columns. So let's add one more column. I'm trying to create some random integers. Let's put some zeros as well. And put some zeros here. So this is a 4-row, 5-column matrix. So let's now, as I said, once you verify that the number of columns in the first matrix is equal to the number of rows in the second matrix, then we can multiply the two matrices. The product matrix will be of dimensions, leaving out the common dimension. It will be a 3 by 5 matrix. Okay. Now, so the product matrix will have 3 rows. I'll just mark them with an X. By 5 columns, so we need to have 5 columns. So that will be the product matrix. So we could determine any individual cell of this product matrix in parallel. In parallel means we could determine the value of any individual cell in the product matrix independent of the process of determining the value of any individual cell in the any other individual cell in the product matrix. So that means if I want to find the value of this cell, which is row 2, column 4, I can do it, I can compute it at the same time as I compute the value for cell row 3, column 2. So we can do it in parallel. So matrix multiplication is a very good example for doing parallel processing. And Julia really is a very strong supporter of parallel processing as well. All right, so we're not doing any parallel processing, but I'm just telling we could compute all these cells in the product matrix at the same time by going through a parallel processing approach. Okay, so let's say now I want to compute this cell in the product matrix, which is row 2. So let me say I want to compute make sure that rule is still there. Okay, so I want to compute in the product matrix row 2, column 4. Okay, so this is the cell I want to compute here. Row 2, column 4. All right, so for that, I need to multiply all the elements in row 2 of the first matrix. That's what the rule says. Row I of the first matrix, we want to focus on row I, column J. So row 2 in the first matrix multiplied with all the elements in column 4 of the second matrix. So that's going to be a pairwise multiplication, which means this 3 here multiplied with this 8. So it's 3 times 8 plus. So that's what I said by followed by the addition of all the product pairs. So this is one product pair plus this 4 in row 2 multiplied by the corresponding element in column 4, which is 4 times 1 plus then this is 5 times this 3 here plus this 4 times this 8. Okay, so notice there'll be 4 such product pairs, and the reason why there are 4 such product pairs is because of the common dimension, that is 4. So you see here, this row will have 4 column values that's denoted by, represented by these 4 columns. So that's this row vector, and this column vector that you have here will have 4 rows. That's this common dimension 4. In the 4 rows in the second matrix. So the row vector of the first matrix, basically the row 2 vector of the first matrix, will have 4 columns, and the column 4 vector of the second matrix will have 4 rows. So you are multiplying them pairwise because the number of columns in the first matrix equals the number of rows in the second, which means the second matrix, a column vector, will get such pairs, and the number of such pairs correspond to the common dimension 4 in this case. So you have to just compute the product and add them up. So it will be like this: 24 plus 4 plus 15 plus 32, whatever that value is. So in this case, it's 28 plus 15 plus 32. Let me just compute quickly. So 28 plus 47, that's 75. So that means this cell value is basically 75. Okay. Now, if I want to compute this one, which is row 3, column 2, I need to multiply the elements of row 3 in the first matrix with column 2 in the second matrix. So it will be this 2 times 5, column 2, plus the 0 times 3, plus the 6 times 5, so the second column in the second matrix, plus 7 times 1. So again, there'll be 4 such product pairs because of the common dimension 4, and you just add them up. So this is 0 here, so this is 10 plus 0 plus 30 plus 7, that will be equal to 47. So this cell is basically 47. Okay, so that's how you can compute all the cells of the product matrix in parallel. Right? I hope this is clear. So let's go back to the code. Okay, we're looking at this eigenvalue stuff. So let's do this. So if you want to multiply this 3, 2, 3, negative 2 with 2, 1, so 3, 2, row wise, 3, 2, and 3, negative 2. That's the A square matrix, and the column vector, you're multiplying it with 2, 1. That's our row vector here that we're multiplying with. Okay, so this is going to be 2 by 2 matrix multiplied by 2 rows, 1 column matrix. So the product is going to be a 2 by 1 matrix. So we can right away figure out its dimensions. So now let's say I want to get this entry, which is row 1, column 1. I need to multiply, so in the product matrix row 1, column 1. So I need to multiply row 1 in the first matrix with column 1 in the second matrix. And second matrix has just 1 column. So it is this 3 times 2 plus this 2 times 1. Row 2, so row 1 multiplied with column 1. So 3 times this 2 here plus this 2 times the 1. And that's going to be 8. 6 plus 2, 8. Now, if you want to get this cell, that is row 2, column 1. So row 2, column 1. So that's going to be this row 2 multiplied with column 1. So it's going to be 3 times 2 plus negative 2 times 1. And that's going to be 6 minus 2, which is 4. So this product matrix is basically 8, 4. And that's what you get if you multiply the scalar eigenvalue with inside the column vector 2, 1. It's also 8, 4. So the equation is verified. So I was trying to bring this up to showcase the property of eigenvalues and eigenvectors of the matrix. So you have for any square matrix A of dimensions n by n, that many eigenvalues corresponding to the n value. So if you have a 4 by 4 matrix, you're going to have 4 eigenvalues, and for each eigenvalue, you have corresponding eigenvector. Like in this case, this 4 is the eigenvalue, and this 2, 1 is the corresponding eigenvector. Such that if you multiply that square matrix A with the eigenvector, again, eigenvectors or column vectors, the product will be equal to the product of, on the right hand side, the scalar eigenvalue multiplied by that column eigenvector. Okay, for each of those eigenvalues and eigenvectors, this property will be satisfied with the square matrix. So let's go to this code here. And Julia has a built-in package or built-in function basically available in the linear algebra package to compute the eigenvalues and the corresponding eigenvectors of the of any square matrix. So first you can call this function eigenvals of matrix. So when you call eigenvals, that's a function name, and you call and you pass the matrix. So here my matrix name is just matrix. So this version of m lowercase m matrix is not any keyword, so you can label your user-defined matrices to be just like that, matrix. And you can pass that matrix as the argument to this eigenvals function. So it's going to return the eigenvalues of that matrix. Again, the lowercase m matrix can be a user-defined matrix. It's not a keyword in Julia, so you can create with such name. And here I'm printing. Again, this is a 4 by 4 matrix, so it has 4 eigenvalues, which are these eigenvalues here. Now, the eigenvalues could be sometimes complex numbers, and we don't worry about that for now. So it could be a real number or a complex number. So there will be just 4 entries. So in this case, this is one entry, one eigenvalue. And this is a complex number. So it has this 32 is the real part of the complex number, and 36, negative 36.71 is the imaginary part of this complex number. And this is a third eigenvalue with this real value and imaginary value. And the fourth eigenvalue with this real component and the imaginary component is 0. Okay, so the eigenvalues could be complex numbers. And for each such eigenvalue, you have eigenvectors which are not available right away as the output of the eigenvals function. The eigenvals function will return only the eigenvalues of the square matrix. So if you want the eigenvectors of a square matrix, then you need to call these eigenvex function and pass the matrix, and that would return an eigenvectors matrix. So it return a matrix of eigenvectors. And if you print that eigenvectors matrix, this is how it's going to get printed. Okay, and I'm printing it using the print matrix function, remember. So this is going to be printed like this. This is basically each row of the eigenvectors matrix. So this is the first row. Let me show that here. So this is the first row of the eigenvectors matrix. This is the second row of the eigenvectors matrix. This is the third row of the eigenvectors matrix. And this is the fourth row of the eigenvectors matrix. All right. And so all these things together are stored in this matrix name, which is eigenvectors matrix. So now, remember I said the eigenvectors are basically column vectors, right? Like this 2, 1 here. So the eigenvectors matrix, as it is returned by this eigenvex function, doesn't return it as column vectors for each eigenvector. It returns like this. So it's up to us now to extract the column vectors. It's there, it's embedded inside this matrix. But if you want to just extract a particular eigenvector corresponding to a particular eigenvalue, it's up to us to do that. So the way this matrix is structured is for each eigenvalue, you have a column vector in this case. So let's say if you pick up the first eigenvalue here, then the first column in each of these rows will correspond to that column vector corresponding to that first eigenvalue. If you want the eigenvector, basically the column vector corresponding to the second eigenvalue, which is 32 plus minus this imaginary part, then in this matrix, you have to pick up the second column. That would be the corresponding eigenvector. Okay, so for that, I have written a function. So extract eigenvector of vectors. So basically for each eigenvalue, we want to extract an eigenvector. All right. We don't need this one. All right. So I pass the matrix as argument to this function, and I get the size of this matrix, which returns the number of rows and columns. So I create a kind of a dummy, or not dummy, initial, it's going to be a vector of vectors. So I want to put in this vector, the entry is also going to be the column vectors. So I want to put the first column vector, followed by a second column vector, followed by a third column vector, followed by the fourth column vector. It's a 4x4 matrix. So I get into this each column because I want to extract column vectors. So I run a for loop corresponding to the number of columns. So for call index in 1 to n calls, and I can get the column vector by this, as I showed earlier. So matrix is the matrix name here, followed by, we want to get all the row values in that column corresponding to call index. So that column, comma, call index will retrieve that column vector corresponding to the column index. And I am storing in that as a local variable column vector. And then I can push that column vector into this vector of all columns. Okay, so the first column vector basically has been pushed to the vector of all columns. And I repeat this process for call index 2, call index 3, call index 4 to push column vectors corresponding to columns 2, 3, and 4. And once I'm done with that for loop here for 4 columns, I can return that vector of all columns. So if you print now this vector of all columns, and that's what this is going to store. So eigenvector of vectors. Okay, so eigenvector of vectors is going to be a vector of all columns. And now you can print each such column vector. So we're going to print it along with this corresponding eigenvalue. So again, the number of eigenvalues will be equal to the number of such columns you have in this column vector, which is eigenvector of vectors. So I can run a for loop where the loop index is, say, the eigenindex from 1 to the length of the eigenvalues, because remember the eigenvalues is also a vector that stores all the eigenvalues. So in this case, it's a 4 by 4 matrix, so it will be a vector of 4 elements. Then I can print the individual eigenvalues by using eigenvalues of eigenindex. And the corresponding column vector can be accessed using the same eigenindex as the column index on this eigenvector of vectors. So if you go back to the output, so this for the first eigenvalue 1, which is this this is the first eigenvalue. That's what is getting printed here. The first column is going to comprise of this in row 1. This is our element in the first column. Then that's what is getting printed included here, 0.278 here. Then this element, the first column in row 2, 0.554394 is included here. And then the third row, this is the first column, and that's what is captured here. And in the fourth row, this is the first column, and that's what is captured here. Okay, so capturing the first column in these 4 rows using that column vector. Then for second eigenvalue of this 32.7 minus 36.7, the imaginary part, okay, again, this is a complex number eigenvalue. The second column for each row will capture that column vector. So that is 0.744. And this in the second row, this one. Okay. And the third row, this one, second column. And the fourth row. Okay, so this is the same here. Now in the fourth row, it's going to be this one. Negative 0.2486, which is here. This imaginary part. And then the third eigenvalue and the corresponding eigenvector corresponding to column 3 in each row, and the fourth eigenvalue corresponding to the fourth column vector corresponding to the column 4 in each row. Okay. That's about eigenvalues and eigenvectors. We'll come back to this in a later module, and I'll probably go over this code again at that time, but I just want to show you how to extract and what's the practical use of it. Last in this previous video, we saw that we can extract row vectors and column vectors. In this case, for eigenvectors, you want to extract you want to extract column vectors from a matrix. So, and each column vector is an eigenvector corresponding to a particular eigenvalue. Now, the next thing I want to show is there is the INV function corresponding to finding the inverse of a matrix. So what an inverse of a matrix means? Again, the inverse exists only for square matrices. So if you multiply a matrix by its inverse, let me just note like that, inverse of a matrix, we get what is called, this I is called the identity matrix. So let me talk about inverse for scalar values. So let's say we have a scalar means just a number, 3. Its inverse is going to be 1 over 3. That's what inverse means for normal numbers, scalars. And the product of value, it could be a real number, it could be an integer, as long as it's just one number, it's called a scalar. So the product of a scalar and its inverse is going to be 1, right? So in this case, the 3 and 3 will cancel out. Similarly, for a matrix, for a square matrix, you could compute its inverse, and the product of the matrix and its inverse would be equal to an identity matrix. So if we have a 4 by 4 square matrix, its corresponding identity matrix will be like this: 0 followed by 0, 1, 0, 0 followed by 0, 0, 1, 0, followed by 0, 0, 0, 1. Okay, so the identity matrix we call the leading diagonal, which is this diagonal, will have all ones, and all the other cells will have zeros. So that's how an identity matrix of a certain dimension will look like. A 3 by 3 identity matrix will look like this: 1 followed by this 0, then 0 followed by this 1, and then 0 followed by this. That's how a 3 by 3 identity matrix will look like. So, for a square matrix A, again, not for all square matrices we can find an inverse. Again, a numerical equivalent for scalars is you cannot find inverse for all numbers, or let's say you can find inverse for all real numbers other than 0. So why you cannot find inverse for 0? Because it will be like 0 multiplied by 1 over 0. 1 over 0 is infinity, so that will not be 1. Okay, so 0 times infinity is not 1. So we cannot find inverse for 0. Okay, likewise, there's something called determinant of a matrix. The determinant of a matrix is a scalar quantity. Okay, so you cannot find you cannot find the inverse if the determinant of that matrix is 0. Okay, so if the determinant of a square matrix is 0, then the matrix is called a singular matrix. So it's a special name for, of course, determinant. I'm not showing here how to compute it, but just know that there is something called the determinant of a square matrix, which we can compute. And if it turns out to be 0, and it's a scalar quantity, as I just say here, so determinant of any square matrix. Again, determinant can be found only for square matrix, and the determinant of square matrix is a scalar quantity. It's just going to be some number. If that number happens to be 0, okay, then the matrix is called a singular matrix. Again, everything refers to square matrix in this case. So we cannot find inverse for a singular matrix. So that means we can find inverse for a square matrix only if the matrix is not singular. So it should not be a singular matrix. That means its determinant should not be 0. If the determinant of a square matrix is 0, we cannot find its inverse. Okay, like we cannot find inverse of 0, like that you cannot find the inverse of a square matrix whose determinant is 0. So if the inverse of if the determinant of a square matrix is not 0, an inverse exists for that matrix. All right. So if you have a matrix, square matrix A, and assuming its determinant is not 0, that means it has an inverse, and that's the inverse. And the inverse of a matrix is also a matrix, and of the same dimension. Okay, so we're dealing with square matrices here. So if the matrix A is of dimension 4 by 4, the inverse of the matrix is also going to be of dimensions 4 by 4. So the product of the matrix and its inverse, since the dimensions are the same. So let's say, for example, this is a 4 by 4 matrix, and the inverse is also a 4 by 4 matrix. The identity matrix is also then going to be a 4 by 4 matrix. So if you multiply a matrix with its inverse, you're going to get an identity matrix. So for any such square matrix that is not singular, we can find its inverse. And this INV function basically will compute that for you in Julia. So we have created here a matrix of random integers, in this case a 4 by 4 matrix of random integers in the range of 10 to 100. And I call the INV function on that matrix. It returns this inverse matrix. Okay, and I'm printing that inverse matrix here. which is this matrix. So this is the inverse matrix of this. Okay, so this is our matrix A that we, or this matrix that we generated randomly. And the INV matrix is basically the inverse of what I have highlighted here, and that's here, this one. Okay, so if you multiply this matrix as the first matrix with this matrix as the second matrix, the product will be an identity matrix. Okay, I'm not showing that here. Let's do that here. So how to multiply two matrices? So let's do that. So multiplying matrix and its inverse. So there is multiplication of function also available in Julia, and it's a very straightforward multiplication. So let's say we can get identity matrix because we know it's going to be an identity matrix. So the star is the function name itself for multiplication, and it takes two arguments supplied within this parenthesis. And two arguments are here, the matrix, the first matrix, and we label the inverse matrix like this. So let's call it as inverse matrix. Okay. And we can print the inverse matrix using the print matrix function that we have. So let's print it. Rerunning it, so it's going to be a new random matrix that gets generated, which in this case 52, all these things. All right, so well, let me see. Let me print. I'm printing the inverse here. Let's see, print inverse matrix. So I'm labeling them so I can figure out what each matrix is representing. All right, so I think I have everything to run this. Okay. So this is an inverse matrix for this matrix here. So yeah, so for this matrix, this is the inverse matrix. So that's a square matrix, and the inverse is this one. So for an integer square matrix, the inverse could have real numbers, that's fine. And then this is the identity matrix. And as you can see, the entries in the identity matrix are like this. The first entry is a 1, followed by all zeros. It's a 4 by 4 matrix. So 1 followed by 3 zeros, then 0. So this is technically 0 because 4.44 something that times 10 to the power negative 16 is almost 0. Then followed by 1. Then again, this is negative 4.44 times 10 to the power negative 16, which is a 0. Then 8.888 times 10 to the power negative 16, which is technically 0. That means the second row is like 0, 1, 0, 0. The third row is 0, 0, 0, so 0, 0, and then a 1, followed by 0. That's the third row of the identity matrix. And the fourth row is 3 zeros followed by 1. So 0, and this is technically a 0, followed by a 0, followed by 1. So that's the identity matrix I was talking about. So we multiply a matrix with its inverse. So this is the inverse of the matrix that we generated randomly. in the beginning, this matrix. Okay. And you multiply the matrix with its inverse, you get an identity matrix. All right. So that's about inverse of a matrix. So now what I am showing is we can also find something called the transpose of the matrix. Okay. So the transpose of a matrix is going to be like this. The rows written as columns and vice versa. And the transpose can be found for any matrix, need not be just for square matrix, could be of any dimension. So let's do it like this. Let's say we have a 3 by 5 matrix. So 3 by 5 matrix could be something like this. 3 rows, 5 columns. So let's say something like this. And second row, third row, so this is say 3 by 5 matrix. If you want to write its transpose, the transpose would be a 5 by 3 matrix. So the first matrix has 3 rows followed by 5 columns. So that's the 3 rows followed by 5 columns. 3 rows, 5 columns. The transpose will be 5 rows and 3 columns. So what are those 5 rows? The 5 rows will be the 5 columns of the first matrix. So that will be something like this. So the first row would be the first column, 10, 52, 85. The first row of the transpose will be the first column of the original matrix. Then the second row, oh, sorry. Let me look at this way. I want to get the first row, right? So the first row will be this way. The first row will be the first column of the original matrix. So the first column written row-wise. So that's this. This is the first row of the transpose. And the first row of the transpose will be the first column of the original matrix. Then the second row of the transpose will be the second row, so second column of the original matrix. So second row of the transpose will be the second column of the original matrix. Then the third row of the transpose will be the third column of the original matrix. Then the fourth row will be the fourth column of the original matrix. Then the last row will be the last column of the original matrix. So this is a 3 rows, 5 column matrix. Its transpose will be a 5 rows, 3 column matrix. Okay, so that's how matrix and its transpose are related. So you could multiply a matrix with its transpose, and the product will definitely be the square matrix because you're multiplying a 3 by 5 matrix, say in this case, with a 5 by 3 matrix. So the rule for multiplication will be automatically satisfied. The number of columns in the first matrix will be equal to the number of rows in the second matrix, and the product will be a 3 by 3 matrix. Okay, so that means you're going to multiply, say for example, to get the first row, first column cell, you're going to multiply the first row with the first column. Okay, then to get the first row, second column, same first row with the second column. First row, third column, same first row with the third column, and so on. Then second row, first column, second row with the first column, and so on. So the product matrix, or the product of a matrix and its transpose will be always a square matrix. Now here, I use the same square matrix that we generated in the beginning, which is here, this matrix, and I'm just finding its transpose. And so we had 54, 43, 19, 28, right? And so on. So let's look at the column here, because the first column of this original is going to be the row, first row of the transpose. So 54, 13, 94, 39, the first column will be now the first row, 54, 13, 94, 39. Then 43, 83, 77, 79. 43, 83, 77, 79 will be the second row. Then 19, 75, 82, 93 will be the third row. 28, 47, 53, 63 will be the fourth row. That's the transpose. Okay. All right. Now, the last thing we'll see in this video. Sorry, this is turning out to be a long video, but I just want to put all the matrix operations together. Is again, like we did matrix multiplication of a matrix with its inverse, we can do a matrix multiplication for two matrices created randomly. Let's change the dimensions a little bit here. So we have some flexibility. So this is a 3 by 5 matrix. And let's say this is a 5 by 4 matrix. So if you want to multiply two matrices, let me add the rule here. To multiply two matrices. Say like this, matrix A times matrix B. Let's put it like this. The number of columns, the first matrix, which is matrix A, should be equal to the number of rows in the second matrix, which is matrix B. Okay. And also the dimensions of the product matrix is then the number of rows in the first matrix, matrix A, by the number of columns in the second matrix, which is matrix B. Okay, so the product in this case is going to be a 3 by 4 matrix. All right, so I'm creating two random integers matrix of dimensions 3 by 5 and 5 by 4. So let's run it again. Okay. So the eigenvector computation is a little time consuming. So you can see Julia takes some time to compute the eigenvalues and eigenvectors. Okay, it's done. So this is the inverse of this square matrix on the top. And it's going to compute its product. It will be an identity matrix. Let's wait for that identity matrix to get printed. That's got printed, will be 1, 0, 0, 0, and so on. So this is now the transpose of, again, the matrix on the top. So far we have been dealing with square matrices. That's why for a differential change, I was changing the dimensions here. So matrix A is now a 3 by 5 matrix. So this is a 3 rows, 5 column matrix. And matrix B is a 5 rows, 4 column matrix. So the product will be a 3 rows, 4 column matrix, and that's what we are seeing here. And we know already how to compute the product, right? You do element-wise, so pairwise multiplication of the rows and the corresponding column, and then you add them up. So like in this case, for example, to get this cell here in the product matrix, 19435, you'll be multiplying. So this is row 1, column 1 in the product. So you will multiply row 1 in the matrix A, the first matrix, with column 1, 64, 66, 99, 56, 29, the second matrix. say to get this cell, which is row 2, column 3, you will multiply row 2 in the first matrix with column 3 in the second matrix. So the number of multiplications, the product pairs will be 5 in this case, and that's the common dimension 5 here. Okay. All right, so that's what it's getting printed, the product matrix. Now, if you want, we can compute the transpose of this product matrix. So let's add one more piece of code here, transpose of the product matrix. And you can compute it by calling a transpose function and pass the product, which is matrix C. Okay. And then you can say println, this is the transpose of the product matrix. You can just print that name, that's good enough. And print that contents of the transpose product matrix. And if you want, we can multiply the, no, we don't need to multiply that. Okay, let's just print the transpose. And since the since now, okay, we can multiply them. Let's multiply them. Okay, let's say it's matrix D. It's going to be the matrix C, that's the product matrix, multiplied with this transpose, which is this. And let's print that matrix D. Now, since it's going to be a square matrix, as I said, the product of a matrix and its transpose is always going to be a square matrix. I can also find its inverse. So this is a revision of what matrix functions we already see. So we can find the inverse of it. So the inverse of matrix D is going to be found by calling the INV function and passing the matrix D as the argument. And we can again print the inverse. Inverse of matrix D. Call the print matrix function. And the product of this matrix D and its inverse is going to be an identity matrix. So I'm not doing that again. So let me start with this on the code and see. Okay, so first we deal with square matrices, and now we are going to the rectangular matrices, if you want to call like that. So this is a 3 by 5 and a 5 by 4. The product is a 4 by 4. It's a square matrix. Sorry, the product is 3 rows, 4 columns, because again, it's a 3 by 5 multiplied by 5 by 4. So it's a 3 by 4 product matrix, and the product matrix in this case is matrix C. All right, so let's go from here. So that's our matrix C, which is the product matrix. And we are finding the transpose of this product matrix. That means the columns in the original matrix will be written as rows. So the 16, 241, 20, 502, 17, 870 will be now the first row. And the second column will be the second row, and so on. So now we multiply the product matrix with its transpose. You're going to get a square matrix. That's our matrix D. Multiplying a matrix C, which was our product matrix, with the transpose, you're going to get matrix D. Then that's a square matrix. And for square matrix, we can find its inverse. And the inverse is already going to be having very small entries. Okay. So it's okay. It's natural for the inverse to have small entries for a very large entries, the matrix D. Now, if you want to curious, you could just multiply this too and see what it comes up with. So you can call print L matrix right away and do this multiplication here, which is going to be the matrix D and its inverse. I'll just print ln, and that's going to be definitely an identity matrix. So it's matrices, you can verify a lot of properties and you can make sure your computation is correct by verifying those properties like we did for eigenvalues and eigenvectors, Ax equals lambda times x. So you see here, the product of this matrix D and its inverse is an identity matrix. It's a 3 by 3 matrix, square matrix. So it's going to be 1 followed by 0 and 0. Then this is technically a 0 followed by 1 and a 0. And this is a 0, 0, 1. Okay, so I'll stop with this.